Hello, today I'll be discussing Lab 5 titled Collisions. The purpose of this experiment is to observe and analyze the collision of two objects of identical mass using the momentum and energy principles. Specifically, we'll be determining the nature of the collision between two rubber balls. We know from previous labs that the net force is equal to the change of momentum over time. In the case of this experiment where we have multiple objects, we sum the object's momentum to get the change of momentum of our system, where our system is just the two rubber balls. And as we see written here. During the brief time interval of the collision, we can say that the net external force is equal to 0. And this is because the interaction between the objects in our system are much stronger than between any other possible agents in the surrounding. Therefore, we get that delta P is equal to 0, or in other words, the summation of the initial momenta is going to be equal to the summation of the final momentum. When applied to the energy principle, we get that the change in energy of the system is going to be equal to the change in kinetic energy plus the change of any internal energies, which is equal to the work of the surroundings. Or work of the surroundings is equal to the force times displacement, which remember, we found out that the net external force is 0, so this makes this expression equal to 0. Types of collisions are characterized by differences in their delta K and their delta E internal. For example, when we have elastic collisions, we get that kinetic energy is conserved. That means that K final is going to be equal to K initial, similar to how we have that momentum is conserved here. Same kind of concept, right? In that case, where delta K is equal to 0, delta E internal must also equal to 0 to satisfy the expression. In the case of our inelastic and fully inelastic, delta K is not equal to 0, kinetic energy is not conserved, so that means there has to be some delta E internal. Now, what I didn't note here is that there could also be some changes in potential energy. For the purposes of our lab, or this lab right now, I don't have that being considered, as you'll see in the observed data. And because I'm not considering it, we can solve for the delta E internal to get this. Right. Using these concepts and assumptions, we can characterize our observed collision. For the observations, I used the app tracker to analyze the collision. An important equation to keep in mind is the equation for momentum, which is equal to mass times velocity, where momentum and velocity are vectors. And I get the vector components of velocity by doing dx dt and dy dt from the graphs, where dt is a very small number. So it's as close to instantaneous velocity as possible. Right. Here we have my video. Keying in on some important frames. Frame 9 is the collision. So I used frame 7 and 8 to get the initial velocity of our first ball, where the second velocity, or the velocity of the second ball, is 0 because it's at rest. Frame 9 the collision, and then I use frame 11 and 12 to get the final velocity. And you can see these points on the graph. This linear section here before the collision, at rest here before the collision. Then we see frames 11 and 12 that I use to get the final velocities. Alright, using our observations and previously discussed formulas, we can determine the characteristics of our collision. So here, delta P is equal to 0. From that, we get this expression, where the second term here is equal to 0 because the second ball is at rest initially. Doing a little algebra, we get 0.28 meters per second. Note there's no kilograms in this expression because all the mass cancel out. It's the same mass on both sides. And then on the right side of the equation, we get 0.24 meters per second. Obviously, these aren't equal to each other. Now, what does that mean? That means that delta K, the kinetic energy, is not conserved. It's not equal to 0. So we have a delta E internal, which we can solve for, which I've done here, to get 6 times 10 to the negative 4 joules. Now, before we just write this off as an inelastic collision, let's consider also the kinetic energy, initial and final. Solving for both of these, I get a magnitude of 10 to the negative 3 as opposed to 10 to the negative 4. So this internal energy is a magnitude smaller. So we could say that on the spectrum is actually much closer to an elastic collision as opposed to a fully inelastic collision, which would have the objects sticking together. However, if we just follow the numbers, we'll call this an inelastic collision, with the internal energies most likely being thermal, vibrational, or potentially sound in nature. And with that, thanks for watching. I hope you have a great day.